Okay, off we go. So, there was a failure of the system, and the TA forgot to put up the attendance quiz, apparently. So we're not taking attendance today. I'm sorry. I didn't know that this was the case until about 2 minutes ago when someone asked me, and I can't get the quiz up that fast. So anyway, apologies for that. But picking up where we left off last time, we were talking about curl, and in particular Stokes' curl theorem, right? And we had, I will go ahead and rewind just a bit. We had this interpretation of curl as an oriented density. The idea is that curl points in the direction that the rotation is around, and its magnitude tells you how much of of the rotation there is as you go in that, as you sort of are looking, for rotation in that direction. And I make the observation, this is really not that weird of an idea, because we've had oriented densities before, and in particular the gradient, right? And I think this is a wonderful analogy, and I really encourage everybody to kind of dwell on this analogy. That in the same sense that you can't really talk about how much rotation you're going to notice until we discuss which direction around which you're looking. It's just like with, if you're hiking out on a hill somewhere and you want to ask how much altitude change, what's my rate of altitude change? It depends on which direction you're going. Right? The mountain has a steepness. That steepness is in a direction, but you might be going a different direction. So even though there is an absolute notion of how steep the mountain is, you're only going to experience to the extent that you're actually going in that direction. So dot products do that for us. Same with curl, right? Curl points in the direction that the rotation is happening. How much of that rotation are you going to experience? Well, it depends. Are you looking for? Is your little piece of surface set up in such a way that its boundary, right, is going around the same way that the actual fluid's rotation is? If it is, yeah, then you'll get it. And if it's not, then, well, not so much. Right? So the analogy is quite strong. And I'll remind you further, since we're already back here, this idea of thinking of curl as oriented density, right? The quantity in question being circulation, of course. So our oriented circulation density, it's morally equivalent, right? Different particulars, of course, but morally equivalent to the idea of thinking of gradient as oriented change density. So use whatever intuition, whatever makes this feel good. Right, new laser pointer. I just wanted to try it out. Whatever makes this feel good. The idea of thinking of gradient as oriented change density, right? To the extent that you digest that, well, that's your guide for how to think about curl. And in particular, how to think about it as an oriented density. So, yes, the particulars are different. Yes, the geometry is different. And yes, curl's a little bit geometrically more challenging. Just because of the geometry, really. Right? But totally analogous. So anyway, I think that's a really important idea. We ended last time talking about fluids. No particular surprise here that curl tells you the nature of the rotation of the fluid and therefore the nature of the thing floating in the fluid. And then likewise, in 3 dimensions, curl is telling you the nature of the rotation of the fluid. Then again, this time in a more complicated way, we have to talk about what axis, etc. And therefore also tells you the nature of the rotation of the thing floating in that fluid. Now, 3-dimensional instead of 2. Okay. All right. Moving along. So magnetic fields. Now, you're going to notice some similarities here to something we've done before. You notice this little square of equations. I write it as this little square of equations deliberately. I mean, we're the role that the divergence theorem played in the previous little square of physics equations that we wrote down concerning gravity and electric fields. Totally analogous. Now, again, geometrically very different, but structurally totally analogous to what we're going to see here using Stokes' theorem to understand magnetic fields, as it turns out. Okay, so here's the reality, and by the way, this is the nature of the physical world. This is not a decision that anyone made, certainly not me, right? But this is not an arbitrary thing that just got decided or whatever. This is empirical reality. This is the nature of how the world is, and we're all a little surprised about it in some sense. So here's the reality. If you have a flow of charged particles called a current field, right? So a bunch of charged particles flowing along. And by the way, let's talk about the term current field. How does that make sense? Current, we've always thought, y'all have probably already always thought of current as being something that happens in a wire. Right? Certainly when I got to this stage of my learning of physics, I always thought of current as, well, it goes through wires, which are basically little one-dimensional curves, basically. Right? Well, if you think about it, all current in a wire is, well, there's a bunch of charged particles that are cruising through that wire. And yeah, we think of it as being basically one-dimensional. It's not exactly, right? I mean, that wire has a little bit of a thickness to it. It's got a cross-section. It's actually a three-dimensional flow. Very narrow, three-dimensional flow, right? But it's nevertheless a three-dimensional flow of charged particles. And this is just saying, yeah, okay, sure, well, let's generalize that. Let's not even worry about whether it's a narrow flow or maybe a wide dispersed flow. Whatever, right? Any flow of charged particles. Analogy. Let's think about mass, right? So very often we treat mass as a point mass. And that too is not really physical. That's not how mass works. Mass, in fact, even if you have something that you treat as a point because it's so small, it's not actually a point. It's actually got a little size to it, and the point mass is just an approximation. And likewise, a one-dimensional curve current is just an approximation of this more general reality that charged particles, kind of move around in 3 dimensions, and they have that flow is not as narrow as we like to pretend it is. Okay. All right. Physical reality, again, nobody decided this. This is just the nature of how the world is. It creates a magnetic field. And let's see here. I gotta think about So that magnetic field for the current field that I've drawn, the magnetic field would be something kind of like this. And y'all may have had an intro physics class. If you have, this might look a little bit familiar. If not, then good. Then when you do take an intro E&M class, you'll be appropriately armed with the math that really is very important in order to be able to make sense out of the physics. So the nature of it is a little bit weird, but there's what they call a right-hand rule. And if you put your thumb in the direction of the current, then the fingers of your right hand will curl around your thumb, right? Point in the direction of a rotation around your thumb that describes how the magnetic field goes around like that. Okay, so again, don't ask me why. I didn't do it. It's the way it is. Okay. All right. So let's, for the moment here real quick, let's talk about a flux. So we could imagine some surface. Let's see here. How am I going to do it? Let's imagine some surface over here. And let's think about, how would we describe the flux through that surface of this current field? And, by the way, yes, there is this constant over here. There's this mu naught constant. Again, it's on both sides of the equation, so it's nothing we need to worry about. We'll get to that in a minute. But if you were to ask, okay, looking at that current field and looking at flux through that surface, that blue surface, now let's think about what that is. Current is a flow of charged particles. Flux says how much of the fluid is passing through your surface. That's the whole point of flux, right? Flux was motivated out of the idea of I have this flow of particles, water, air, wildebeests, whatever, right? I have this flow of stuff, and I want to know quantity per unit time passing through my surface. So what is the flux of the magnetic field? Well, it's literally the number of charged particles. Oh, whoops, wrong color. The number of charged particles per unit time going through your surface. And you may recall, now again, if you've had a physics E&M class before, if not, then what we call charged particles per unit time going through something is current. That's what current is. Okay. All right. So, sure. Again, this little mu naught constant, don't worry about it, doesn't matter yet. So, now thinking back to, what do we know about magnetic fields? And again, this is just an empirical observation, right? But current, yes, it creates this circulation of magnetic field. It makes a magnetic field that kind of goes around, right, and sort of in circles, in loops, let's call it. And empirically, we can just observe that more current makes more magnetic circulation. It just does. Again, nature of the world, I didn't do it. Okay, then we look at this circulation and think, hey, we have an awesome theorem about circulation. Boundary circulation is flux of the curl of whatever it is that you're looking at the circulation of, aka it's the flux of circulation density, and thus curl. And then, all together, we look at this integral we now see being equal to this integral, and this is true for all possible surfaces. Oh, I wanted blue there. It's true for all possible surfaces. Pick your surface, and the only way that would make sense is if, in fact, the integrands are equal. Right, so a bunch of physical setup, but what this gives rise to is a pretty neat observation. First of all, this is called Maxwell's fourth equation. Again, how you number Maxwell's equations is not, it's arbitrary, right? Anyway, so I call this Maxwell's fourth equation. And likewise this, also, Maxwell's fourth equation. And again, they look different. One's about current and magnetic circulation. One is about the flow field of charged particles and the curl of the magnetic field. And so again, they appear to be different things, different statements in some sense, but they are connected, very strongly connected, so strongly connected by Stokes' theorem, right? That we actually call these the same equation. These are both Maxwell's fourth equation. They're basically the same equation in the same sense that Maxwell's first equation has kind of two different forms. They're morally equivalent, right? Likewise here, two different forms. They're kind of morally equivalent. Okay. All right, so a little bit of physics there. Again, this isn't really a physics class, but gosh, it's a fantastic physical metaphor. In fact, let me click back here to when we were talking about electric fields. Here we go, electric fields. Here's the analogous thing for electric fields. And remember, electric fields are really morally pretty much the same as gravitational fields. Right? Basically the same. The only difference is constants and units. Boring, right? But I like to think of this as that the physical universe was kind of thoughtful enough to create a physical manifestation, a physical model for divergence. Right? And it's very simple. Mass creates this gravitational field. Right? We're all comfortable with that idea. Mass creates a gravitational field, and as a sort of a model for how to think about divergence, looking at that gravitational field, again, that we all experience viscerally on a day-to-day basis, what is the divergence? It's mass density. Right? The way mass works, the fact that mass is distributed and has a density, that is divergence. That's what divergence looks like. Right? Physically manifested. Thank you, physical world. It's fabulous. Right? Gravity and likewise E&M are just wonderfully convenient physical metaphors for divergence. So that's something to think about. Take a little time, let that kind of soak in. And along those same lines, now less useful because, gravity is so relatable. Right? Very, very relatable. We all understand gravity in some sense, or at least in the local, surface of the earth sense. But very relatable idea. To be fair, magnetic fields, not so much. Right? But at the same time, this is a physical metaphor. To whatever extent you feel like you understand current and the resulting magnetic fields, it's a physical manifestation of how to think about curl. So, for your consideration, kind of neato. Okay. So, going back to Stokes' theorem, and let me go back a few pages. Here we go. Stokes' theorem. That's equal to this. Useful in various ways, magnetic fields, etc., flows of fluids, rotations of floating objects. As a tool for computing line integrals, which we might want for various different reasons, right? Useful in a lot of ways. And it has a price tag. It has a condition. The vector field's got to be C1. It's non-negotiable. Everywhere, to emphasize, right? As said differently, we are not allowed to have singularities. If any sort of singularity problem, it's going to really mess up the computation. So that's what we're going to see in the next example. I just want you all to see it kind of happen. Here is a vector field, and it's a useful vector field to know something about. Comes up a lot. One thing you're going to notice is that the curl is 0. Easily computed. You got to take some derivatives, right? Partial derivatives. Good little exercise, though. I encourage you to give this a try. Compute that curl. It ends up being 0. Well, that is everywhere except for the z-axis. Now, on the z-axis, x and y are both 0, which means the vector field doesn't even exist. It's undefined. Right, so here's our singularity then. Right, so this vector field does not make sense on the z-axis. Now, how does this show up in the real world? Well, imagine a current through a wire, and imagine the z-axis is a wire. Right, that current through the wire is going to feel a lot like it's a one-dimensional curve through which current is flowing. And again, not really. Wires all have a little bit of thickness, right? Maybe not much, sure, right? But a little bit, right? So in the same way that mass always has a little bit of size. Yeah, okay, right, but we treat it as a point mass because it's close enough and it's convenient for various purposes. Likewise, here, this is not a current. Well, physically, when you're talking about current through a wire, it's not exactly what I'm describing here, because that would be literally a one-dimensional wire with no thickness. Not what we're talking about, right? But nevertheless, this is an approximation of current through a wire and the resulting magnetic field.
And so here's the problem. These things are supposed to be equal. Right? Stokes' theorem, these things are supposed to be equal. Problem is, if you were to compute a line integral around any one of these curves, and I drew a couple of concentric circles, not that you have to, right? Same thing works for any other curve that goes around the z-axis one time, like I have drawn here. You compute that circulation and you will get 2 pi, right? But if you look at the surface, whose boundary that is, and if you compute this flux of curl, and then if you remind yourself, well, yeah, you know what? The curl actually is 0 everywhere inside here, everywhere. Well, except for, not at the origin, right? The origin is its little problem, right? But it's just the 1 point. Who cares about just 1 point? It's only 1 point. How much difference could 1 point make? One might speculate. Curl being 0, seemingly close enough to everywhere, you would think that these two integrals should be equal, but they are not. You get 0, again, kind of ignoring that 1 point. How much difference could that 1 point make anyway? And so we have, depending on how you define flux and how you deal with nasty little issues that I'm sweeping under the rug, looks like Stokes' theorem has failed. And it's because of one little singularity. Now, reminder, let's go back to when we were talking about something along these lines with gravity. Nope. Wait, where is it? Nope. Hang on. It wasn't gravity, it was light bulbs. Right? We were talking about something similar with light bulbs, and we were imagining not a point mass, but we were imagining a point LED, right? And that single LED that we usually think of as being physically, well, in fact, that is physically just very, very small. If we were to consider the limit as it gets smaller and smaller and smaller and consider it as a point light source, then we got an analogous kind of problem, right? And the resolution of this seeming problem was that we had to admit that while the divergence is 0 everywhere, that suggests light source density was 0. Well, yeah, but there's a discrete lump of light source, namely where flux comes from. There is that single point, right? And if you were to pretend in some sense that it, rather than source being distributed, flux as an accumulating quantity being sort of smoothly distributed over that entire interior, if you think of there being a lump at that one geometric point, then that fixes the problem and everything kind of fits and everything sort of works and makes sense. And so analogous to that, let's see here, going back to where we were, going back to here, the same sort of thing, dimensionally a little different. Rather than thinking of the fluid as flowing, through a wire like that, we were thinking instead of, but fluids actually flow, there's always a little bit of a thickness to the wire. There's always got to be some sort of dimension to the fluid. If you were to allow yourself to imagine a single, it's like a focused stream, except it's like a lump. It's just that this is a one-dimensional lump, and so I'm going to call it a focused stream of circulation. Yeah, it's kind of like circulation density, but it's a lump of it across this wire. A little bit of a weird way to think about it. But that focused stream of circulation, right, you will notice fixes the problem because that goes kind of in with where circulation density was. This is just a lump of circulation, as opposed to a circulation density. And that is what makes these sort of match up. That'll turn this into a 2 pi. When you fix all of this, right, formally in ways that I don't think are appropriate to this class, that actually does make everything work. So, and then again, now, does this actually make physical sense? Well, if you go back to the light bulb, again, if I can remember where it is. Yeah, you go back to the light bulb. Physically speaking, how do we think of that lump of flux? What I'm claiming is like as if there's a single geometric point concentrated lump of flux in there, and that makes our accumulation of flux add up to the non-zero that it's supposed to be. How do we think of that point? Yeah, it's a point mass. Right? The point mass creates the point lump of flux. And in the same way, how should we think about this focused stream of circulation? It's the current, the one-dimensional, current in a curve, in a one-dimensional curve that is our kind of, metaphor for thinking about current in a wire, right? Which again, not really one-dimensional, but we like to think of it as being one-dimensional. So that makes this work out in the same way. So again, sticky issues, nasty little business if you have singularities, and do be careful with singularities in that sense. But it is fixable in these cases. Okay. All right, moving along. So y'all remember this theorem. This is the what I call the local test for path independence, or a local test for whether or not a vector field is a gradient. Very important, of course, to know if a vector field is a gradient. You want to make sure, let's see how to say this. If you know that a vector field is a gradient, if you know that there is an anti-gradient, well, then it doesn't seem outrageous to look for it. Right? On the other hand, if you know that there is no anti-gradient, your vector field itself is not a gradient of something. There is no anti-gradient. Don't try to find it. There isn't anything to find, right? And so the way we resolve that question, we saw, again, this local test. And the local test is that the question that we're asking is entirely resolved by looking at the curl. And if the curl is 0 everywhere, then yep, all good. And if it's not 0 anywhere, then don't bother trying to find the anti-gradient. There isn't one to be found. Okay, so we talked about this when we were doing Green's theorem, and because if you look at the way the calculation goes down, the way the argument goes, we had previously established this that being a gradient in the restricted category of appropriately regular. Let's not worry about discontinuities and singularities. Let's keep everything nice and C1, right? That said, being a gradient is the same as being path independent, which is, by the way, the same as saying that all your circulations are 0. And so we just made the cool observation from Green's theorem. One of the different color. Green's theorem says that that's equal to that. And that's the perfect thing that gets us over here to the right, where we make arguments about how can an integral always be 0. Well, that means the integrand must have to equal to 0, and we get to this result that curl is our local test. Okay, so that's very quick because it was review. At the time that we did that, I made a vague reference to there being an equivalent. Well, I guess I stated it anyway, that in the same way that two-dimensional curl is the test in 2 dimensions, that 3-dimensional curl is the test in 3 dimensions. And semantically, maybe that sounds believable, right? But semantics is not something you can trust, right? So how do we know that this is true? And at the time I said, well, we don't really have the tools. Now we do. We do have the tools at this point. The tool that we need to make this second argument is Stokes' theorem. So in the same way that we start with gradients being path independent, being vector fields where circulation is zero, in the same way that Green's theorem allowed us to relate circulations to double integrals of curl, in that same way, Stokes' theorem in 3 dimensions is the thing that allows us to relate circulations to now surface integrals of curl, which now, of course, is a vector field, not a scalar. And so, yeah, a little different, right? But really analogous in important ways here. Oh, gosh. I want that. There we go. Okay. So, by the way, I do a lot of this, what I'm about to refer to here, but I'm sure you've noticed, I like to, when calculations really are truly analogous to each other, I like to lay them out on the page analogously to emphasize the comparison there, right? So, to whatever extent you feel like you understand how Green's theorem worked in that 2-dimensional argument, well, that's your cue that Stokes' theorem works in an analogous way, adapted appropriately, of course, right? But that's kind of to be expected. That any, whatever role Green's theorem played, Stokes' theorem plays here. Okay. And then, again, if an integral is 0, the integrand must be 0. Likewise, if all of these integrals are 0, then the integrand must be 0. And so there's our local test, just like in 2 dimensions, there was our local test. So, now this is just filling in a blank that we had left back in chapter 6. Just nice to finish a gap that I had promised we would finish later, and here we are. Let me pause here for a second for questions. Is everybody okay with that? Okay. We've already done examples with this. We've done examples, a couple of examples where, we had questions as to, hey, is this a gradient? Is it not a gradient? That is it path independent? Is it not path independent? And we saw one where it's resolved by computing the 2-dimensional curl, and then we saw one where it's resolved by looking at the 3-dimensional curl. Okay. All right. So, moving along. Okay. This is a new idea. Or you might say just a kind of an application, kind of an extension of an old idea. And the first thing that I have up here is just a sort of a compact summary of path independence. Now again, we've seen path independence before, so I know y'all have already seen this. Hopefully y'all are already comfortable with the idea of path independence and this sort of a picture that we did some cool stuff with, again, back in chapter 6. So quick reminder, the big idea up here is if you agree on what the starting and ending points should be, and we got to keep that fixed. That's the deal. Fix a starting point, fix an ending point. Well, if you have on the one hand one curve along which you compute a line integral, of course with the correct starting point and of course with the correct ending point. And if you have another curve, of course with the same starting point and of course with the same ending point, along which you compute another corresponding line integral. The property of being path independent. Path independence means that those integrals will always be the same. Not all vector fields have this property. Cannot emphasize enough. Some, actually very few in some sense. It's a very special property for a vector field to have. But some vector fields have this feature that no matter which blue and green curves you pick, boundaries agreeing, of course, you'll always get the same value for the line integral. It's wild. It's totally unexpected. But again, certain vector fields have this amazing property. And said differently, green equals blue, as we discussed, is equivalent to saying that the circulation going all the way around is 0. Okay, so I hope that all looks familiar. The reason I'm reminding you of that stuff is that this is a perfect analog of the next thing we're going to talk about, which is called surface independence. And I love this little property. I think it's very, very cool. I think it's the natural extension of the idea of path independence. We're going to see the details in a moment. And it's a fabulous little computational tool, by the way. I've used it many times in physics calculations that I had to do, right? This is an important deal, right? Computationally very valuable. And yet, to my surprise, my perpetual surprise, most multivariable calculus textbooks don't even mention it. I think that's super weird. What I needed of multivariable calculus when I was y'all's age, right, and heading into a collection of courses that were going to be about the physical world and electricity and magnetism, expected to come up quite a bit. For example, fluid flows expected to come up quite a bit. Surface independence is definitely an idea that I really needed, right? And it never came up in math classes, which I just thought was super weird. Anyway, here it is. And again, I've laid things out deliberately for the purpose of emphasizing the strength of the analogy here. Now, instead of two curves with the same boundary points, we're going to talk about two surfaces with the same boundary curve. It's sort of one dimension higher, analogous. Right? Two surfaces with the same boundary curve. And let's go ahead and write down these surfaces. So the first surface we'll call S1. Some surface. Now I've got to orient it like so. Oh, by the way, I need to orient that curve as well. So we've got this S1, sort of if you will, above the belt line there, the top part of that surface there. S1. It's got the correct boundary. And then also, we can talk about the bottom, below the belt line, this S2 surface kind of down here, if you will. And oriented also upward. And again, you got to make sure it's got the same boundary as the green surface. And if you play orientation, remember we have very specific rules about how if you have an oriented surface, what is the resulting orientation on the boundary, and think about which way it has to go to make that purple boundary orientation agree, and it has to go also upward, just like the green orientation is pointing upward. Now, real quick before I go on, if I say the green is oriented up and the blue is oriented up, okay, that sounds kind of the same in some sense. But if I were to phrase it as the green is oriented outward and the blue is oriented inward, that makes it sound like they're kind of opposites. So which is it? Are they the same or are they opposite? It's a little bit of a disturbing, wait a second, it seems like we've got a little contradiction here. And in fact, we don't have a contradiction. What we have is a bad question. You can't compare orientations on different surfaces. S1 and S2 are totally different surfaces. How do we compare? They barely agree on any points. Right? So really, in fact, there is no question. At the same time, you have, I'm sure, this sense of a feeling of you're going to want to decide, wait a minute, are they the same? Are they different? Let's go back up to the top again. This orientation in blue is what you might call to the right. This orientation in green is what you might call to the right. And in that sense, they feel like they're kind of the same in some sense. But wait a minute. This one looks counterclockwise. Well, this one looks clockwise. And they're kind of different in that sense. And so it's totally analogous. Now, I hope you're not weirded out by, you look at that top picture up there and you see we've got this curve, we've got that curve, and they're both sort of upward and to the right in some sense, but on the other hand, the green one is counterclockwise, the blue one is clockwise. Okay, well, yeah, sure, but that's just how you choose to look at it, right? There's no mystery, right? Hopefully there's no mystery up here. So I just want to point out, it's totally analogous down here. Right? Yeah, you can think about both of them being upward. Yeah, you can think about one being in and one being out. No mystery. You're just choosing to think about a comparison in different ways. Nothing to worry about. Let me pause on that real quick. Are you all kind of okay with this? The resolution of this seeming contradiction, the seeming sort of inconsistency. All right. So we've got analogous setups. And in the same way that there is this idea called path independence, where amazingly, assuming all the rules are satisfied, the line integrals must be the same. Shocking. Likewise, there is this concept called surface independence, and it's exactly the same thing. If I were to look at the green surface integral and the blue surface integral, surface independent vector fields amazingly have this amazing feature that you'll get the same surface integral, no matter which two surfaces you pick. It's just like path independence. Just with surfaces instead of curves. How we doing? Everybody with me? Satisfying? Okay. Right. And by the way, in the same sense that you can think of the equivalence of two line integrals as being a circulation having to be zero, likewise you can think of these two fluxes being equal. You can think of as the statement about closed fluxes, boundary fluxes equaling zero. So again, also analogous. Very, very similarly. Okay, so that's what surface independence is. Now, I think it's kind of amazing that these ever happen at all. Let me say it differently. This is one of the biggest intuition turnarounds I have ever experienced in learning math. Like where you go from, wait a minute, this couldn't possibly be true. Oh no, wait, it's obvious. Right? And I love it when that happens. It's intellectually you feel like you just broke through a mental barrier. And this is one of them. I mean, you look at path independence. How could that be? How could anything be path independent? That's crazy. They're totally different curves. What do you mean the line integrals are always equal? It's insane. Oh, wait a minute. That's going to work for every gradient. Of course it is. Gradients you compute with the fundamental theorem of line integrals at the boundary point. So of course, right? Likewise with surface independence. And I'm going to talk you through sort of why even though it looks like it shouldn't be possible, it's actually, once you take the right point of view, an immediate consequence of a theorem that we already know. And again, I'll flesh out those details in a moment. Before I do, I want to go back to the diagram. You all remember this diagram that I made? And I'm a big fan. Again, this takes a bunch of very, very natural, sophisticated, powerful ideas that are way too much to talk about here, and boils off all the formality and all of the rigor and all of the sophistication and just gets down to, okay, yeah, but how should I think about these things? And I claim if you organize all of the ideas that we're talking about in Chapter 7, as laid out on this diagram, everything fits together
It's just the coincidences won't stop. The analogies just keep on coming. It's wild.
So let me remind you what we've previously discussed about special vector fields in position 1. The special vector fields were gradients. Namely, they have an anti-gradient. Said differently, same thing. There are vector fields whose curl is 0. Said differently, there are vector fields that are path independent in the sense that if you take any two curves and that have the same boundary points, that you'll get the same value for the line integrals. Again, this is how I like to draw that. In the same way that these three conditions are all simultaneous. Again, regularity issues ignored. Let's assume everything is as nice as we need them to be. No singularities, no nonsense. Green, blue, and orange, always simultaneous. You have one, you have the other two. It's awesome. In that same way, everything slides over one notch, and everything still works. Let's see, I guess I'll do it. It's the layout's a little bit different. We have special vector fields in column 2. These special vector fields are curls. They are vector fields whose divergence is 0. They are vector fields that are what we call surface independent. Namely, you have any two surfaces. You see the layout of the diagrams. It fits perfectly. Any two surfaces with the same boundary curve give you the same flux. Right? That's exactly how we describe surface independence. And the connections between these is extremely analogous. Now I'm going to come back over here real quick and I'm going to remind you, how did we see, let's see here. How did we see that gradients are path independent? And vice versa, at least part of the vice versa. Fundamental thermal line integrals was our insight there. And how did we see that curl being 0 gives you path independence? We did that earlier today. Stokes' curl theorem was the thing that made that work. All right, so here's the further amazing fact. Not only do the results translate over, oh gosh, I'm in trouble. No, too big. Gosh. Okay, I'm just going to have to do this a little bit more carefully, sorry. Just a little bit. Oh, come on. There, okay, got it. Okay, in the same way, that it was the fundamental thermal line integrals previously, it's now Stokes' theorem, and the same way that it was Gauss's divergence theorem that was Stokes' curl theorem previously, it's now Gauss's divergence theorem. Let me say that a little bit differently. The pattern of which theorems should help us prove what results also holds. Not the same theorems, but the analogous theorems. And so we're about to see this. We're about to see how we're going to use Stokes' curl theorem to show that curls are always surface independent. And we're about to use Gauss's divergence theorem to show that a local test of surface independence is divergence being 0. So now what I'm showing you here, again, I think this is very, very valuable. I've made the observation before. This diagram, everything fits together. Everything kind of goes where it should be. Patterns hold, and you can use that pattern to guide you at how to figure stuff out. Right? In the same way that we know that the way we connected these two ideas when they were back here was the fundamental theorem, the analogy suggests we should think about how to use Stokes' theorem to draw this conclusion. And likewise for the other. So let's see here now. I believe I have, let's see. No, I am out of time. Okay, so that's set up for where we will pick up next time. And what we will do next time, you'll notice we're going to use Stokes' theorem and we're going to use the divergence theorem. See y'all later. Have a good one.